Alright, practice problems for variance in heredity. Variations in heredity. So, first one example here, we have a breed of cow, and we know that their traits, this particular trait for color of their fur is going to be codominant. So we're going to use capital R to represent red, and we're going to use capital W to represent white. So the first part says, what would the phenotype and genotype ratios of the offspring be if you took a red cow and a white bull? So if you had a red cow, what would make it red is that it has two alleles for red. And if you had a white bull, it must have two alleles for white fur. So we can set up our Punnett squared here, and we can say, okay, if we combine these two, we could have our WR, our W for the matter, WR for this one as well, if they inherit the red coloring from their mother and the white coloring from their father. Same thing, they take the white coloring from their father and the red coloring from their mother. Same thing here. So the question is, what would the phenotypes be? And if we look at the offspring, 100% of them, or 4 out of 4, again, it is just a percentage or a ratio, are going to have a roan coloring. That's basically roan coloring. That is the coloring of both red and white at the same time. They're codominant. That is their phenotype, the description of what they look like. Their genotype, all of them, again, 4 out of 4, another way of saying 100%, or they're all of them completely. 4 of the 4 are going to be heterozygous for white and red coloring. We refer to that as being roan as their phenotype. Part B says, what if you took a roan cow? So let's do RW or WR, doesn't matter. With a roan bull, so they would be heterozygous for both the red and the white coloring. So again, we can set up our Punnett square here for this combination, and you would end up with, if you took the red allele from the mother and the red allele from the father, the offspring would be red. If you took the red allele from the mother and the white allele from the father, we would have a roan offspring. Same thing if we took the red allele and the white allele here, we would have another roan offspring. But if we took the white allele from each of the parents, we would end up with a white offspring. So we have a 1 for red to 2 for roan, this one and that one, to 1 ratio of red offspring to roan offspring, which is, again, is a codominant trait, so it would be expressing both at the same time. Roan to white, and that is a 1 to 2 to 1 ratio. Next example saying, looking at blood types, and so we have a woman who is AB, and she has some children with someone who is type A. So we know that the mother is type AB, and this is a 2 allele. So we know that one allele is definitely the A, and one allele is definitely the B. But the father of these offspring, all we know is that they are type A. So type A blood, if you were to be type A, there's two ways to be. You could be type A with both alleles being A, or you could be type A blood with one allele being A and one allele being O. So you don't know which one of those two it is. But if we look at the children of these two, we see that one has type A, one has type AB, and one has type B. So type A is easy to explain. If you take the A allele from the mother and A allele from the father, that child is definitely going to be type A. Type AB blood, again, if you take the type A from the father, and since the mother's AB, you take type B from her, the B allele from her, that would explain type AB. So we have type A explained, type AB explained. However, if there is a child from these two that is type B. The only way you could get type B blood would be if you took the allele B from the mother, and you couldn't take the A from the father because that would give you AB type blood. So that father must be not homozygous for type A, but must be heterozygous, and so it must have inherited an O allele from the father, a B allele from the mother, giving it type B blood. And then we can work this one out here. This offspring here, we get the A allele from the mother and the O allele from the father. And so phenotypically, we'd have two type A bloods, one homozygous and one heterozygous. We'd have one type AB blood, and we'd have one type B blood. So from those parents, we get these combinations. So the genotypic ratios of the children, we would say that there is going to be a 1. We know what the genotype of the father is now. He must be type AO. We'd have 1 AA, we'd have 1 AO, which would have the same phenotype, type A. We'd have 1 AB and 1 O. And again, this is just a probabilities of ratios, not necessarily what's going to happen. They could have all 4 children ending up with, sorry, I said type O, type B, which is heterozygous for O. So again, it is a probability of type A, type A, type AB, and type B, heterozygous for A, and heterozygous for type B, in a 1 to 1 ratio, type AB, which has to be heterozygous, and then homozygous for type A. So those 4 possible combinations. Example 3, we have a rooster here with gray feathers mated with a hen of the same phenotype, so gray. Among their offspring, there's 15 chicks that are gray, 6 that are black, and 8 that are white. What's the simplest explanation for the inheritance of these colors? So if we have these 3 traits, it must be codominance if we have gray, black, and white. And so we have a combination between these 2 parents. So let's imagine a Punnett square that would probably be able to explain this. But if we imagine that we have these 2 traits, let's say B for black and W for white, that could be one parent, and if it's codominant, they'd end up being gray. And if we have the other parent with the same phenotype, they're gray as well, maybe the same genotype. If they were to breed, we would have this offspring here with both of the black alleles from each parent, so that offspring would end up being black. This one would have 1 black and 1 white, as well as this one here. So about half of the offspring would end up being gray if this is a codominant trait, and we would still have some offspring showing up with white coloring as well because they have inherited that trait from their parents. So if we looked at the numbers here to see if that works out here, we have a 1 to 2 to 1 ratio of black, let's sorry this out here, black in a 1 to gray, which is twice as prevalent, to white, looking at their genotypes. And looking at these numbers they give me the question here, they're saying that 6 are black, was it 15 are gray, and 8 are white, which is not perfectly 1 to 2 to 1, but that's how statistics work. You'd have to have a giant sample to get exactly 1 to 2 to 1. So with a 1 mating of these chickens here, that's a decent ratio, pretty close to a 1 to 2 to 1 ratio. So looking at this, the fact that they are codominant for black and white traits is the best explanation. What sort of offspring would you get if you mated a gray rooster? So if it is codominant, a gray rooster would have to have both black and white traits. And if it is with a black hen, it would have to have homozygous for those traits there. So then we look at this Punnett squared, the 2 B's would come together. Same here. So those 2 offsprings would be homozygous for black, and then we would have the black and the white traits coming together. And so you would end up with a genotypic ratio of black to gray. There's 2 black to 2 gray. So we would say it's in a 1-to-1 ratio, 2 to 1 if you like.